I know you're anxious about the grades. I wish I could tell you what they are, but this ain't something I can fabricate now. I can only tell you, I'll get them back to you. Some people ask me this in different ways, but it's the same intent. Is there going to be a curve? Well, I don't even know what the grades are, so I can't even think about something like that. First, I got to get the grades before I say anything, so please just don't ask me about this over and over again. I'm just leveling with you. I have no earthly idea how things went. If you want to know how I made it up, I went through the homework problems. So I literally just scalped things out of there, changed maybe a resistor value, or maybe the orientation of things, but that's the only thing I did the entire test. If you look, when you get it back, if you want the problem number, come see me. I'll give you the problem number that I got. All right, that said, and I do apologize too, because I would want that scores, but I mean, honestly, this is a big old class. I don't know if there's over 100 still. There's probably, we started with 115. There might be over 100, and he's got a grade. Well, this class, I don't know what else he has to do, but he had plenty to do between today and Friday. And as soon as I get him, I'll put the grades up, and I'll send you all of them. All right, so that's the only thing I can say for sure. Now, having said that, one second. All right, so this is on page 258 of the book. We're talking about three-phase power. And I want to try to make this as easy as possible. So what I want to tell you is this. With three-phase power, you're going to be tested on this. And you'll get a quiz on it. But I'm going to try to tell you one thing. If you can listen to me before I even start. You're going to take everything that's any of the circuits I'm about to show you, you're going to reduce it to one single phase. That's what we've been doing. And it will be the Y-Y connection. Now I'm going to explain everything I'm saying now. But everything gets reduced to the Y-Y connection. And remember that, and then everything is the same as before. Remember the power factor, remember complex power, all that stuff, line voltage is the same, but you have to get it to that point. So what I'm going to do is show you a typical Y-Y configuration, and then a delta-delta configuration. I'll show you how to transform the delta into a Y. For the Y, this is going to be a Y source, Y load. This is always the source side, and this is the load side. So what that means is the source has three phases, same identical voltage, but they're all separated by 120 degrees. So you're going to see something like this drawn in the book. I gave you the page number. And I'm going to call this the A phase. So they use small a's for the load. The center here will be what's called the neutral or ground. This is going to be the B phase point, and this is the C phase point. This will be plus to minus, and this is called VAN. A is with respect to this point, N is here. Whenever you see VAN, it means VA minus VN. That's all it means. As a matter of fact, I'll put it up here. If you have VAN, that's simply VA minus VN, and so forth. Now, I'll add more detail, but this is not that difficult. So this voltage, whatever it is, has what's called a phase, V phase, and it's going to have an angle. Now, whatever that angle is, all the other angles would be 120 degrees different from this. So I'm just going to say V phase at 0 degrees. Phase is a voltage, it will be an RMS. All power stuff is in RMS. This B phase will be plus to minus VBN. It's going to have the same magnitude as this, but the angle will be plus 120 degrees. Y'all follow me on this? And he puts this in degrees, not radians. Finally, the C phase, you'll notice the plus is at the point where C is, and then the negative is at the neutral or ground point. And VCN is going to be equal to V phase. Here they'll put minus 120 degrees. If you want, you can put plus 240. They are the same point mathematically. Do you understand that? Minus 120 is plus 240. That's all it is. All right, now they're going to be connected to a load here, and it's a Y configuration. So over here, when I say Y configuration, it means you're going to have 3 points as such, and you're going to have a neutral, and then you're going to have this. I better make this a little bigger. You're going to have some ZY here, ZY here, and ZY. Y is simply the thing that designates the type of configuration the loads are in. And this is ground, this is the neutral here. Now these points are given capital letters, and it's just an arbitrary, there's no real reason for this, but the only reason they do that is the capital letters are associated with the load, and the small letters with the source, and it doesn't have to be that way. Other books may change it. But if you look, well, he shows us on page 262 in the top in figure 8.36. He doesn't draw it the way I do. But I want to be clear about this. The reason I show you like this, that looks like a Y. It's obvious to me. Sometimes the way they configure these things, you're not sure exactly what the configuration is. This is a Y. I think everybody can see that. Now, anytime you have this, and by the way, does anybody remember from, I think it was a lecture before the test, where I talked about why there's 120 degrees of phase difference for these voltages? Anybody remember this? Yes. Go ahead.
Because it's 3 phase.
Well, yeah, but yes, sir. See?
Because 120 times 360.
I'm not sure if you're implying what the right. The reason is because the power at these loads, when summed together, will always be constant. There is no variation in the power used by all 3 loads. Total power, you understand? That means if the power here being dissipated is a constant, and it will be for the 3 phases, not for one phase. For one phase it goes up, down, up, down, up, down. But for all 3 phases, because they're exactly 120 degrees out of phase, when you add up all those powers, you'll get a constant power. And that constant power means the load on, and I'm not going to get into the way they do that, on the generator. Does everybody realize these large turbines, if you're mechanical engineers, you can appreciate this, they're rotating. They would like a constant loading. They don't want a load that is changing with time, even though it's a high frequency change. The reason is any kind of jitter like that will cause problems. You don't want things with enormous amounts of inertia and the possibility of shearing a shaft on one of these things to have any kind of variation if possible. You'd like it constant. Now, not just, this is just one load, but in fact, a power company, a real power company, would be targeting a huge number of 3-phase loads all over. And so they would like all this power to be a constant, so there's no variation. Y'all, that's the fundamental reason for 3-phase power. Now, getting back to this, there's also something you have to consider. Any connection between a phase, this is a phase voltage, and the load here goes through a line, and the line has losses. You've already seen that for a single phase. Do y'all remember this class? So here, if you have A, it's a little tough to draw this, you're gonna have some line impedance. I'm gonna call it Z line. The designation doesn't matter. And they assume in these circuits, they're called balanced three-phase. What that means is the same exact load value is here, here, and here, and the same exact line impedance is on all three lines. Y'all follow me on this? Now the lines, the A, small a is connected to large A there. For B, I gotta route this thing and do this. It's just showing a jump. Well, I'll put the Z line here. You're gonna have Z line here as well. And it will be connected to B here. And finally for C, you're gonna have this. As such. Follow me? That's the YY configuration. And this one is the easiest, and that's why we take everything you're going to see, which is delta delta or delta Y delta, and always take them and turn them into this, and I'll show you how. Y'all follow me on this? It's very important that you appreciate that's the goal of this, because this is the simplest circuit to analyze. So the thought is why? We simply take the A phase. The only thing you do is going to take the A phase and analyze it. And this one you've done already. So this is V phase at 0 degrees, and I'll show you what I mean by this. Here's going to be the line impedance, whatever it is, and then you're going to have a load, and this is ZY, and it's grounded, and this is grounded. So this is the A phase. Sometimes you'll see A phase, it doesn't matter. It's indicating we're talking about 1/3 of the circuit. So all values for power that you get, or complex power, will be multiplied by 3, and that should be obvious to you. With me? Now, if you look at this, it depends what they specify. Usually, they specify this. They'll specify the value from here to here, and you can call that I call it the line voltage. So I'll just say it's V line here, and it will be something, and it'll be like V, I'll just call it VRMS at some angle, theta RMS. Actually, it's usually 0. I mean, anytime it's not 0, it's just asking you to think more deeply than you need to. So that's the voltage. Then here, just as before, the load here will have some average power, whatever that is, and it will have a power factor, and almost always it's lagging. Now, in the real world, I can't think of a single case where you don't have a lagging power factor, because most of the industrial loads that use three-phase. Has anybody worked around large textile mills or anything like that where they have three-phase power coming in 480 volts? Anybody? Anybody? Well, you have dryers that are 240, right? They're really what? Just plus or minus 240. It's only a single phase. It's not three-phase. But if you work around anything with a lot of power, where they need a lot of power to drive motors or turbines or something, there'll be three-phase motors and things of that nature to drive conveyor belts or something that's going to be a mix or something like that. So anyway, this is what they usually have. They'll have average power. Let me draw that a little bit larger so the people in the back can see. Just as before, they'll have an average power at the load. They'll have a power factor, and it will be lagging. And now, they may want the usual business. They may, and we'll just go through it. If you wanted the current here, all right, I line, you'll notice here, everything's in series, it's a single loop. You follow me? So the current through every component is the same, right? How do you get the current? It's always keyed here, right? You're going to say the average power, as before, is equal to this VRMS, whatever it is, times the magnitude of IRMS, times the power factor, or the magnitude of IRMS is simply average power, as before, divided by VRMS times the power factor. That gives you the magnitude. You just had the test, so you know this. If this has an angle of 0, how do we get the angle of the current? I assume people did pretty well on this, but I don't know for sure. You take the inverse, what? Cosine of the power factor. So I take cosine minus 1 of the power factor, and there's one other thing I do. Put a negative there, right? Because it is lagging. So it's going to have a magnitude, I'll just call it magnitude, IRMS, and it's going to have that angle. Now you got the current, right? After that point, it's just like before. If you want the voltage here, right, the only thing you're going to do is what? Take the voltage V line and add to it Z line times that current. Do you all follow me on this? If you do and understand, just raise your hand so I know. You understand that, don't you, class? And once you had that, if you wanted the power factor here, you'll just take the cosine and the difference in angles between the voltage there. If I put V phase at 0 degrees. You really don't know what this is. Maybe I'll just call it VS and it's a single phase. Now you can take a look and find the magnitude and the angle there. So you can find the actual power factor at the source, correct, class? Finally, the last thing is the complex power for one phase. And the complex power is just V, I'll say for the source, V source times I source conjugated, and that will have a real power here. So it'll have P plus JQ. And the real power, if you think about that, we can get, if we know VS here, and we know IS, and now I'm just assuming that, then I know when I look at this complex power for this source, is going to be whatever this is in magnitude, and then it's going to be whatever, actually I can do it that way. I can just say, it's going to be VS, and it's going to be at the angle of theta S. It's times I conjugates, so it's going to be I RMS, but it's the angle is going to be equal to theta I, it'll be a positive value for that, so it's going to be a positive cosine of the power factor. And that will give you the complex power. It's going to have an average power and an imaginary or reactive power, a JQ. You'll follow me on this? It's just as before. So if you want the total complex power of this system supplied by the system, it's just going to be 3 times that. That's my whole goal. It's just to show you, you analyze one phase and you multiply by 3. That's it. Everything is multiplied by 3. You all follow me on this one? How many understand this? It's really not hard, but you have to be attentive here. Now, if that's the case, what happens when we have a delta configuration? So I'm going to erase that and put a delta configuration I'm going to show you, so you'll understand how to transform it. We always want to go to this and do a single phase analysis, and I'll do one today. Hopefully. Now, the difference between a delta and a Y phase, the real difference is there is no ground shown anywhere in a delta configuration. So I want you to follow me on this. This is important. What you're going to have are sources. I got to see where this is shown in the book. Let me show you the Y phase. All right, this is on page 260 in figure 8.32. Now, it's done in a sparse way, too. It doesn't really go through all the details, but I will. So here, you're gonna have 3 points as before, A, B, and C. And then you're gonna have a voltage here, V, A, B, and this is a delta network, plus or minus. You're gonna have a voltage here. B, B, C, and then you're gonna have a voltage here. B, A, C. And, or you can do it this way. See, I'm looking for a picture of a delta voltage in here. Well, he doesn't show it the way I'd like to, but anyway. So this is the source configuration delta. You'll notice, yes, sir.
How do we know the orientation of the voltage sources? Will that be something that's given to us?
Well, the A, B, and C will be shown, all right? And whenever you look at these, they'll have a plus indicated. If you notice this VAB, this is this voltage minus this voltage, right? This VB, yeah. This VB, hold. AB, actually, I have this drawn. This should be this way, plus, minus, and this should be plus, minus, CA. I'm sorry. What I'm getting at is the A is here. This would be the plus sign. The first thing, this is the thing that's subtracted from VB. This is here. This one is V. Yeah, VC would be plus, minus, and VCA would be plus, minus. But you can change the orientation. If you wanted VAC, the plus sign would go here. You'll see in a second that all these things have one thing in common. They're going to be 30 degrees of, or 120 degrees of separation between these. But here's the one thing you got to get. This is a delta voltage. So V here, VAB, is actually going to have a magnitude, and I'll show you this in a second, the square root of 3 times the phase voltage of VAN, or you can take magnitude of VAN here, and the angle here is going to be the angle of VAN. Almost always that's at 0 degrees, but it's going to be at 30 degrees more. Now let me just show you this. I'm trying to do this vectorially. It's on page 261 in figure 8.34. Some of this is a little weird, but you're going to have to follow me. So if I look at VAB, I have to do this. I'm going to call this the real axis, and this the imaginary axis. Now I'm going to go back to this, and I said VAN is V phase at 0 degrees. Do y'all follow me, class? So let me just, and I'll try to be clear as I can about this. So here's VAN. Right there, it's at 0 degrees, and the magnitude of this is just V phase. Then I have VBN right here, right? That's at 120 degrees. Same magnitude. So here, I got something has a magnitude of V phase, and this is VB, but the angle here is 120 degrees. Can you all follow me on this? This is how you represent these things so your mind can actually understand what's going on. This is called, it's in the complex plane This is the imaginary or J-axis, this is the real axis. And I'm just plotting these voltages with magnitude and phase. Now, if you look at VAB, that's actually VAN minus VBN. Can you all follow me on that? How many understand? I mean, mathematically, if you have a VAB is VA minus VB. Here, VAN is VA minus VN. Then it's minus VB minus a minus or plus VN. The neutrals cancel. You get VA minus VB. How many see this right here? Y'all with me? I'm just trying to be as simple as I can about this. Now, if you take a look at this, if I take VAN and I subtract this, the way you subtract vectors, I hope this isn't somebody asking about their test. The only thing you have to do is take this and you simply rotate it 180 degrees, then add them. You all remember doing this stuff, class? If you subtract vectors? So this would be minus VBN. And now if you look at this right here, oh, it's tipped the tail. Give me one second. Should be up here. Should actually. Give me 1 second. I'm just taking a look. Oh, he has VBN as minus 120. Sorry. Let me just say one thing about this. This isn't going to be consequential. This can be minus and this can be plus. It doesn't really matter. In this book, he's got VN as minus. It has to be 120 degrees phase separation. That's the only requirement for this to work. He's put the negative sign there. So actually, this would be 120 degrees, and this would be VBN, and it has a magnitude of V phase. Now, when you take VN minus VB, you're going to get this. And you're going to get this. And this will end up being 60 degrees. Now, this will be VAB. Sorry, the way he did it in the book is different than his prior work. There has to be 120 degrees of phase separation, but he, for some reason, took VN as a negative 120, not a positive. That's his business. It won't matter one bit at the end of the day for everything we need to know. Anyway, this is VAB. Now, the length of this thing, if you actually do this, you're going to find this projection is going to be the cosine of 60 times V phase. This projection will be the sine of 50 times G phase. Just with me on this one, class. If you go ahead and square this side, take the square root, you end up with this. It's going to be equal to square root of 3 here times V phase and magnitude, but the angle will be 30 degrees ahead. That he shows correctly on page 281. What that also implies, and I'm looking for where he's got it laid out clearly. What it implies is this, and this is something I want you to write down, because I want to do a problem, because you'll see how this works. So we've got the light fixed. remember this. Here's a relationship. If you have VAN, the relationship, let me go this way. VAN at any angle, and I'll call it theta AN. This is a Y situation. If you want a delta situation or a delta load, now this is important. You take the magnitude of this, by the way, we'll just say is going to have some V phase at some angle, theta AN. The reason I'm doing this is AN there indicates the phase voltage. This is the angle, almost always at 0 degrees. I'm trying to level with you about this. Over here, when you go to delta, you're going to have to take square root of 3 times the phase voltage or times the magnitude of VAN. And the angle here will be that angle plus 30 degrees. You all follow me? Now, something I'm going to say right now. If you are asked to find the other phase voltage, say VBN, the only thing you would do is say not VBC or better yet VBN. In other words, the next phase, same magnitude, and I don't care if you put plus or minus 120 degrees. It doesn't matter, as long as there's 120 degrees phase difference. Do you all follow me on that? That's the reason asking questions about the other phases makes no sense. They're all going to be symmetric, just out of phase by 120 degrees. So I don't even bother, but I will ask for the magnitude of that, and that is, this right here is going to be VAB. All right, so here you have VAB and you want VAN in magnitude, you divide by the square root of 3 and subtract 30 degrees. In other words, VAN and its angle, whatever it is, theta A, and is equal to VAB's magnitude divided by the square root of 3, and the angle is going to be whatever theta AB is minus 30 degrees. I'm just showing you the relationship. There's a 30 degrees phase change and a square root of 3 factor in magnitude. That's all it is. You with me, class? Now we're going to talk about the load. So this is the sources, how they transform. When you see a problem done, it'll be a lot clearer. But when we have a load, and this one pay attention to, you'll need to understand. So if we have, and this is a Y configuration, here's A, here's B, and here's C. Let me put this. Now we have a delta configuration to worry about. So if you look at this, if I take a look at the value of the impedance between these 2 points, you following? So if I measure the impedance between these 2 points, does everybody see it's simply 2ZY? Because that third leg isn't connected. How many see that right there? It's just going to, these two would be in series. That is not connected to anything, it's dangling. So I can say 2ZY equals, now be attentive here. The value of the impedance, if it's a delta connection from here to here, between these 2 points, which will have to be the same in both if they're equivalent, would be what? It would be Z delta in parallel with 2Z delta. Do you all see that, class? This is in series to this point. these two are in series, but they're in parallel with this point. How many see that? Back there, can you guys see the far back? So I'm gonna say this is gonna be Z delta in parallel with 2Z delta. Now I'm simply gonna equate them and I'm gonna find a relationship between Z delta and ZY. This is important. So if I take a look at this, I take 2ZY equal to, and for this one, that's 2 times, and I'm going to take this times this, or 2 times Z delta squared. Remember, I'm taking this one times this one. Let me do it this way so you can see it. I'll take Z delta times 2Z delta over 3Z delta. Now, I just took first impedance times the second over the first impedance plus the second. You all remember that, class, when you have parallel? How many do, right? With me on this one? All right. When I look at this, that's a Z delta squared, so that means I simply have 2 Z delta, right, over 3 is equal to 2ZY. And you can see ZY, and this is the kicker, ZY is simply Z delta over 3. Can you all follow me? There's no phase change there. Everybody see that? So now, let's do a problem the way it should be done based on that knowledge. When you see it applied, it'll be clear. All right, this is problem 833. I want to talk this one through before I just show you, write a whole bunch of stuff on the board, confuse people. Actually, I'm going to start with problem 8.32 first. So this is problem 8.32. And they say they want the equivalent of these two. And it's a per phase. It says the impedance of a Y. So they have three phases. The Y impedance is 4 plus J3. And the delta impedance is 18 plus J12. They want the equivalent Y load and equivalent delta load. Okay. But we're only going to need to do one phase. So here's the deal. Normally, you would have A, B, C, A, B, C. One would be Y, the other delta, but the A's would be connected together, the B's and the C's. So we're going to transform this into both of them being Y and get the equivalent value. Do you all follow me on this? So if the load is capital A and here's the neutral, this one's already in Y configuration, so it's simply 4 plus J3. This one, what do we have to do with Z delta to put it in terms of ZY, class? Divide by 3, remember that. Divide by 3. So over here, we'll take that, 18 plus 12, and divide by 3. I'm showing you it. Plus J12 and divide by 3, just so you know what we're doing. All right, so we want the equivalent here. Z equivalent. Everybody follow me? I didn't divide it just so people watching that are here can see exactly the method I'm doing. Taking 18 by 3, so now I can say, if I look at this, I have 4 plus J3, and it's in parallel of 18 by 3 is going to be 6 plus J, 12 by 3 is 4, and I have these two in parallel, and I need the parallel value of Zn here, which would be equal to Zy. Can you follow me? How many understand what I'm doing here? Do you or not? I've divided this by 3 because that was a delta, and I'm putting it in terms of a Y load. Remember what I told you, everything goes back to the Y. You want the load, whatever it is, if it's delta Y, if they have a delta in parallel with Y, or two deltas, you have to transform that into a single Y load. It's the same with the source. So I have these. How do you get the parallel combination, something like this? Easier to multiply one times the other or one plus the other, right? So if you do that, what do you get? You get the equivalent ZY equal to what? 4 plus J3, if somebody can do this for me, I'd appreciate it, over 6 plus J4, then you have to add them, so you get 10 plus J7. What's that going to be? Let's see. 6 times 4, 24, 3 times 4 is 12, 36. And then you got plus J, what is it going to be? I'm sorry. Got that wrong. So it's going to be 24 minus 12 is 12 plus J, 3 times 6 is 18. And so what, can somebody give that to me? Anybody? Just take, if you want to do it that way, it's fine. What did you get?
2.4.
Plus
1.72.
J 1.7. Can anybody second that? Anybody? Okay. Now that would be the Y equivalent of those two in parallel. You with me, class? Because remember, we're talking about 3 phases, so each phase is in parallel. And we're going to only do one phase. That would be the equivalent Y. What if you wanted the equivalent delta? Multiply by 3. Yeah, I think most people knew that. Right? Just remember that. That's as simple as it gets, but they're going to have loads that are in parallel. One delta, one Y. You're going to always have to reduce it to a single load that's in a Y configuration. Now, if it was connected to a source that was a delta, then you would have to transform that into a Y. I have a little more time. I looked at that problem. It's just talking about the load. So 833, I'd say, is a problem that really showcases almost everything you need except the sources of Y array. So we're going to do 833 in 1 second. Then I'll let you go. All right. So for this problem, we have a few minutes. Let's apparently not put this zooming out of here, but here they said they have an ABC phase balanced load. It is in a Y configuration. So the source is Y, and the load has a delta, and the delta load is 30 plus J12, and the Y is 12 plus J9. They want the currents in the line. This is a classic problem. It's the kind of problem you would get from me. So the source is Y, and let me just see what the source voltage is. So it's 100, and VAN is 180 at 30 degrees volts RMS, which is weird. So they said VAN is equal to 180 volts at an angle of 30 degrees, and it's RMS volts. So first thing we have to do is when we're drawing the single phase, I always recommend you draw the circuit. This voltage is 180 at an angle of 30 degrees. It's RMS. There is no line impedance here, so don't put it there if there's nothing. Now we've got one that's ZY 12 plus J9. This would be small a, this would be large a. So it's equal to 12. And I'll draw this plus J9. And it's in parallel with Z delta, but we have to take that and turn it into an equivalent Y. Do y'all follow me? I'm just trying to make sure I underscore the clearness. I'm clear to be on this one. Divide by 3. 30 by 3 is 10. And now I have 12 by 3 is J4. Y'all with me? That's the equivalent. Now, usually, this is the Y, this is a Y source here. We've changed everything to Y there. Usually, there is some line impedance you have to worry about. But here, there's not, is there? So if I wanted the total current flowing here in the line, I'm asking you something. If I wanted this, magnitude and phase, how would you get it? There's two ways that I see, or maybe more. Anybody? Say, well, Z, right? It's not just R, it's real and imaginary, right? Impedance. Yeah, and that would do it. I'd say, well, the current down here is just this voltage, 180 over 30 divided by 12 plus J9, and the current here would be 180 at 30 divided by 10 plus J4. Do you all agree with that? And you would add them together. Now, how many see that? I'm not trying to just hold you. You with me? Anybody not understand that? Because they are in parallel, they would be additive, the currents through this line, right? Or, how else? Anyone? How about we get an equivalent load, right? We could do that. We could take this times that over this pluses. Either one will get you that will get you the equivalent impedance. And then when I take VAN, or 180 by 30 and divide it, I will get the line current. Do you all follow me? Now, here's one. It's a step ahead. If I asked you for the complex power consumed by both of those, how would you do it? Think for a second. Well, what is complex power? It's the voltage across the component. You're interested in complex power value, and it's times the conjugate of the current, right? Follow me? Do we know the voltage across these two? Right there. Correct, class? Would we know the current if we did the problem right? Yes. So you take that voltage, which is at 30 degrees, 180 at 30, and multiply it by the magnitude of the current, and then you'd have to conjugate the angle or change the sign of the angle, right? And you would get a value with a actual magnitude and angle. Do you all follow me on this one? That is a typical question that I ask. I'm trying to be clear about this. on quizzes and tests that people tend to stumble over because they forgot how to do that when they're doing this problem, if it's not specifically asked for. I warn you about this. Oftentimes, there are questions asked about topics that were covered earlier but are applicable to the problem at hand, like this one, complex power. You clear on this, everyone? Try and be clear. I want to do that. And the last thing I'm going to say, I'll give you some problems that we'll go over on Monday. I will go over, if I have time, I'll go over your test when I get back. And I do apologize, but honestly, there's nothing I can do to force him to get it here without possibly causing your grades to go lower. So, I don't want to do it. That's my feeling.